Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, I'm Celine Dian Sitorus and I'm the student of Engineering Physics ITS with the student's number of 023118400007 as the member of the Instrumentation System subject Class B who lectured by Dr. Suyanto STMT. And for today's video, I would like to review an analog electrical instrumentation with the title DCS or Distributed Control System, Controllers to Output Current Loops. Assalamualaikum warahmatullahi wabarakatuh. Halo semuanya, perkenalkan saya Celine Dian Sitorus, merupakan mahasiswa dari Teknik Fisika ITS dengan NRP 023118400007, merupakan peserta mata kuliah Sistem Instrumentasi kelas B dengan Dosen Pengampu Bapak Suyanto STMT. Untuk video kali ini, saya akan memberikan review dari Instrumentasi Elektrik Analog dengan judul DCS, Distributed Control System Controllers to Output Current Loops. Selamat menyaksikan. Okay, we're gonna move on to the first part of this video, which is the introductions. Under these introductions, there are also several parts, and I'm gonna explain the first part, which is the backgrounds. A 4 to 20 milliampere current loop signal is frequently used in industrial environments to transmit measurements across long distances, such as the temperature of a process or the pressure in tank. This type of signaling is preferred because of its simplicity, noise immunity, safety, and ability to traverse grid length without data corruptions. These current loops are also low-powered systems, since relatively low current transmit the data. Previously, whatever power was not used or lost in the signal transmissions was merely dissipated in the transmitter. But now, with the modern integrated circuits, even the small amount of a power can be harnessed to support necessarily function in these systems. And the next part is the problems. A large number of sensors that take in and translate data from the real world into electrical signals are analog sensors, and if listed as digital sensors, it's because they have integrated analog to digital converters. Traditionally, wired sensors have altered an electrical current in response to environmental conditions. Sensors range from familiar examples like photodiodes and photomultipliers that produce current when exposed to electromagnetic radiations to submersible pressure transducers that are used to measure fluid levels. The standard current signal is used today for industrial and environmental sensors, typically wired to programmable logic controllers or PLC, is 4 to 20 milliamperes, with 4 milliamperes representing 0% of the measured value and 20 milliamperes representing the 100% of the measured value. And the next one is aims. When transistors came into wide use, they would reliably operate at a low value of 4 milliamperes, so the industry standards shifted to 4 to 20 milliamperes. The standard for 4 to 20 milliamperes was originally published in 1966. Current signals are often used in sensors because the current response is usually more linear than the voltage response. Current signals are also typically provide a low impedance for sensors with the benefit of better immunity to noise. One practical consideration is that current signals can extend much further than the voltage signal, allowing robust signal wire length of up to 1000 meters. Power supply voltages used with 4 to 20 milliamperes DC loops vary depending on the applications. However, the power supply needs to be at a 10% higher potential than the voltage drop of the combined components in the circuits. Most 4 to 20 milliamperes loops use 2 wires, but there are also 3 and 4 wire configurations that separate a positive supply from the output connections. The components of a 4 to 20 milliampere loop includes 1. A sensor, 2. A transmitter, 3. A power source, 4. A circuit or a loop, and the last one is a receiver. So we're coming up to the last part of the introductions, which is contributions. The basics of a 4 to 20 mA current loop systems, which gonna show in the next figure, provide several benefits in industrial applications. First, the current loops are simple circuits requiring only a crude power supply, a transmitter to make the measurement, and the source, the current, a wire, and a receiver circuit. The power supply needs to provide only enough voltage to overcome the various voltage drops in the systems. Any excess loop voltage is just dropped across the transmitter. Due to the low current, this is only a small amount of power, which creates a little heat. Second, the current loop contains only one loop for current flow. Therefore, from Kirchhoff's current law, the current through all the elements of the loop is equal. This provides high noise immunity, which is critical in industry environments. The third, safety is provided since the lowest signal level is 4 mA. If something in the loop is broken or become disconnected, the receiver reads no current, which demonstrates a fault instead of the lowest signal value. And the last one, as long as the power supply voltage is high enough to overcome system voltage drops, the desired current representing the measured signal is maintained by the transmitters. Thus, smaller wire gauge with their higher voltage drops and lower costs are used for the interconnections, requiring only an increase to the supply voltage. Most importantly, the relatively large voltage drops permitted across the wiring allow a large amount of wire to be used. This allows physical separations of the instruments being measured and the control room that process the measurement, providing safety to those in the control room. Okay, we're coming up to the main part of this video, which is the explanations. Under the explanations, there are also several parts, and the first one that I'm going to deliver is the basic concepts. Figure 1 shows you a typical 4 to 20 mA current loop system. A semi-regulated 24 VDC source provides power to the current loop and to the transmitter element. The transmitter measures the signal of interest, such as temperature, pressure, and many others, and outputs a 4 to 20 mA current that is proportional to the signals. This current passes through the wiring to a receiving system. There, the current develops a voltage across a resistor that is read by an analog to digital converter, or ADC, and then further processed. The loop is complete with a connection back to the voltage source that powers the loop. So the next part of the explanations is the warp principle. The simplest form of 4 to 20 mA current loop is the type used to represent the output of a process controller, sending a command signal to a vinyl control element. Here, the controller supplies both the electrical power and the signal information to the vinyl control element, which acts as an electrical load. To illustrate, consider the example of a controller sending a 4 to 20 mA signal to an I to P, or current to pressure signal converter, which then pneumatically drive a control valve. This particular controller has two digital displays, one for process variable and one for set point, which a bar graph for displaying the output value. One push button provides the operator with a way to switch between automatic to manual modes, or A to M, while two other push buttons provide means to decrement and increment either the set point value in automatic mode or the output value in manual mode. Inside the controller, a dependent current source provides the 4 to 20 milliamperes DC current signal to the I2P transducer. Like all current sources, its purpose is to maintain current in the loop circuit regardless of circuit resistance or any external voltage sources. Unlike a constant current source, a dependent current source, represented by a diamond shape instead of a circle shape, varies its current value according to some external stimulus. In this case, either the mathematical function of the controller or the arbitrary action of the human operator tells the current source how much DC current it should maintain in the circuit. For example, if the operator happened to switch the controller into manual mode and set the output value at 50%, the proper amount of DC current for the signal percentage would be 12 milliamperes, exactly halfway between 4 milliamperes to 20 milliamperes. If everything is working properly, the current in the loop circuit to the I2P transducer should remain exactly at 12 milliamperes regardless of slight changes in wire resistance, I2P coil resistance, or anything else. The current source inside the controller will fight as hard as it has to in order to maintain this set amount of current. This current, as it flows through the wire coil of the I2P transducer mechanism, creates a magnetic field inside the I2P to actuate the pneumatic mechanism, produce a 9 psi pressure signal output to the control valve. 9 psi being exactly halfway between 3 psi and 15 psi in the 3 to 15 psi signal standard range. This should move to the control valve to the halfway positions. In some process applications, the final control element is reverse acting, in that a controller output current value of 4 mA tells the FCE to go to its full or 100% capacity, and a controller output current value of 20 mA commands the FCE to go to its minimum or 0% capacity. Such is the case with an I2P transducer driving an air-to-closed pneumatic control valve, where the valve spring works to push the throttling mechanism open and air pressure on the valve diaphragm work to push the throttling mechanism shut. A practical reason for designing a control system like this is if the dictates of process safety require the valve to go wide open if ever the instrument air supply fails or the 4 to 20 mA output signal circuits fails. In such applications, we need to configure the controller in such a way that the output display, digital readout, and or bar graph is reverse indicating so as to avoid confusing any human operator using the controller. Since 4 mA represents a wide open control valve and 20 mA represents a fully shut control valve, a reverse indicating controller will display 0% output when the current signal is 20 mA and 100 outputs when the current signal is 4 mA. For example, the control display is a direct representation of control valve stem positions, not of the current signal itself. It should be noted that the direct or reverse indication on the control's faceplate is unrelated to direct or reverse control action of the controller's algorithm. The former is merely the way in which the output signal is graphically represented to the human operator, while the latter in the relationship between the process variable signal and the control's output signal unnecessary for negative feedback control. For the sake of the argument, this control's automatic action could still be direct, even though its output bar graph indication is reversed in order to faithfully show valve stem position to the human operator. And the last part of the explanations is the applications. The details of the controller's internal current source are not terribly important. Usually, it takes the form of an operational amplifier circuit driven by the voltage output of a DAC, or digital to analog converter. The DAC converts a binary number, either from the controller's automatic calculations or from the human operator's manual setting, into small DC voltage, which then commands the op-amp circuits to regulate output current at a proportional value. The scenario is much the same if we replace the I2P and control valve with a variable speed motor drive. From the control's perspective, the only difference is seen in a resistive load instead of an inductive load. The input resistance of the motor drive circuit converts the 4 to 20 mA signal into an analog voltage signal, typically 1 to 5 volts, but not always. This voltage signal then commands the motor drive circuitry to telling it to modulate the power going to the electrical motor in order to drive it at the desired speed. Here, the variable speed motor drive is a high-power electronic circuit that takes three-phase AC power in and converts it to DC power at a variable voltage. That voltage level controlled by the 4 to 20 mA signal from the controller output. Another style of a motor drive is one that takes in AC power and outputs three-phase AC power at variable voltage and frequency to power an AC induction motor. This latter style is usually called a variable frequency drive or VFD, but it looks the same to the controller outputs, a fixed resistive load accepting the 4 to 20 mA output signals. Okay everyone, we're finally coming up to the last part, which is the summary. A large number of sensors that take in and translate data from the real world into electrical signals are analog sensors. A 4 to 20 mA current loop signals is frequently used in industrial environments. This type of signaling is preferred because of its simplicity, noise immunity, safety, and ability to traverse grid length without data corruptions. The simplest form of 4 to 20 mA current loop is the type used to represent the output of a process controller, sending a command signal to a final control element. Control sending a 4 to 20 mA signal to an I2P or current to pressure signal converter, which then pneumatically drive the control valve. The application is much the same if we replace the I2P and control valve with a variable speed motor drive. From the control's perspective, the only difference it sees in a resistive load instead of an inductive load. The input resistance of the motor drive circuits converts the 4 to 20 mA signals into an analog voltage signals, typically 1 to 5 voltage, but not always. These voltage signals then command the motor drive circuitry, telling it to modulate the power going to the electric motor in order to drive it at the desired speed. But in some process applications, the final control element is reverse acting, in that a controller output current value of a 4 mA tells the FCE to go to its full 100% capacity, and a controller outputs current value of 20 mA commands the FCE to go to its minimum or 0% capacity. Okay guys, we're coming up to the last parts of this video. Thank you so much for everyone who've been watching this video. I hope everything that I delivered today would give you insights and give you useful information and knowledge. So everything that I delivered today, I got it from the reference that I will show to you in this video. I think that's all from me. Thank you everyone for watching, and I'm sorry if I had mistakes during the process of making this video. Wassalamualaikum warahmatullahi wabarakatuh.